We are still talking about greedy algorithms, and I'm going to solve a couple of more problems. The next problem is interval coloring. What is the problem? This is kind of similar to the interval scheduling. You have n different activities or jobs that each of them has some specific interval, needs to be done at some specific time. And we wanted to color all of these intervals, all of these activities, so that if there is two intervals which are incompatible, which have conflict, they have two different colors. So, for example, in this example that I have here, these 11 different intervals, one optimal solution is this. And as you can see, I'm using 5 colors to color all of the intervals, and this is optimal. This is the minimum number of colors we need to color all of them. There are many use cases for this problem. For example, assume in a university you are going to schedule n different classes and you wanted to schedule them in the minimum number of classrooms. There are plenty of applications for this optimization problem, actually. So the problem can be solved using greedy algorithm. That's why I put this problem in this set. But how we are going to actually look for the greedy strategy, I need to write down some template. Just assume that we ordered the activities we ordered the activities based on something. Okay, this is the question, based on what? Okay, and then what we are going to follow this template. We ordered the activities based on some order, which is the question for us now, and we wanted and then for each activity, each job, I will assign a color, and then the next activity will be colored with the first available color. Okay, there's a question that how do you know that what is the first available color? That's why actually I put the question mark here, but this is something that we can discuss about it later. Let's just assume that we know how to find the next available color at each step. So the main question for me is that how we are going to find that order. This is going to be that greedy strategy that tells me that if I ordered the jobs based on this specific order, I can just each time take one job, give it the next available color, and just schedule it at that classroom or color. Okay, so what are the greedy strategies that we can consider? I have written 4 of them here. For example, sort all the activities based on the finish time. This is actually something like the strategy that we used, the optimal strategy we used for the interval scheduling in the. And this the next strategy is sort the activities based on the length of the intervals, based on the shortest, from shortest to the longest. The third one is sort the activities based on the smallest number of conflicts, so based on the number of conflicts in increasing order. And the last one is to sort the activities based on the start time. You can see that we have seen all of these activities for the other problem, and we saw that the first one was optimal. Now let's see these strategies for this problem. You see that the problem is different. Here we are going to color all the intervals, not finding the maximum number of non-conflicting jobs or intervals. So I'm going to look at the first strategy, sort the activities based on the finish time. Is it going to give me the optimal answer? Is it going to be the optimal strategy for this problem? If I find a counterexample, I can just reject it. And yes, there is a counterexample for this greedy strategy. If you look at these jobs, if I sort them based on the finish time and color them based on that, the earliest finish time is for this job, right? So just assume that I'm going to use the color 1 for this, okay? And then the next earliest finish time is this one. Because there is a conflict between the job, this job and the previous one, so I cannot use the color 1, so let's use another color. So I need another color, let's just call it color 2. The next earliest time is going to be the next actually earliest finish time is going to be this one, right? I need to color this job. And what is the color which is available? You see that there is no conflict between this one and the first job, so I can use the first color. So I'm going to use the first color for this one as well. The next job to be colored is this one, I mean the last one. As you can see, it has conflict with this job, and it has conflict with this job as well. So color 1 and color 2, both of them cannot be used. I need to use the third color. So in this way, this strategy tells me that I have to color all of these jobs with 3 colors, although I can find the optimal answer with 2 colors. So I can color this one with, let's actually just use the same. For example, color number 1, let's just give a number to the colors. And this one with color number 1 as well. This one with color number 2. And there is no conflict. This one is color number 2 as well. So there was an optimal solution with 2 colors, but this strategy gave me 3 colors. The next strategy was sort the activities based on the length of the intervals, from the shortest to the longest, for increasing order. Is it going to give me the optimal answer? Is it the optimal greedy strategy? Unfortunately, no. There is also a counterexample for, I mean, there are plenty, but one counterexample is this. So based on this strategy, the first one that will be colored is this one. Let's just color it with, for example, the color 1. And the next one is going to be this one. There is conflict. I cannot use the color 1 for that. So I will need to use a different color. The next one is going to be this one, right? There is no conflict with 1 or 2. You can actually use 1 or 2, any of them. Both of them is going to be okay, but let's always stick to the smallest color number. So I can color this one with 1 as well. You can use color 2 as well. There's no difference. And the last one is this one. As you can see, this one has a conflict with both color 1 and 2. I need another color for this one. Again, this strategy is giving me 3 colors, although I can color them using only 2 colors. And what is the way to color them? Use color 1 for this one and color 1 for this one, and use color 2 for this job and color 2 for this job. So I could color it with just 2 colors, color all of them just using 2 colors, but this one gave me 3, so this is not optimal as well. The next greedy strategy was sort the activities based on the conflicts in increasing order, based on the smallest conflicts first. Again, is this one going to give me the optimal answer? Unfortunately, no, and I can find a counterexample for that. So based on this strategy, the first job that will be colored is going to be, let's actually calculate the conflicts first. This one is going to have conflict with just one other. This one is going to have conflict with just one other job. This one is going to have conflict with two jobs, and this one is going to have conflict with two jobs. So the first one is going to be either this one or this one, then this one and this one. Okay, so let's color them. So we are going to give color 1 to this, and the next one is this one. There is no conflict between these two, so I can use the same color for this one, right? Then I'm going to color this one or this one, doesn't matter which one. I'm going to actually show you both. So because there is a conflict between this one and this one, I need a different color, right? And the last one, I need another color because there is a conflict between this one and this one and this one and this one. So you can see that it doesn't matter if you colored this one first or this one, both of them have the same conflict. Anyway, you need 3 colors, although the optimal answer again is 2. And the last strategy was to sort, remember it was to sort the intervals based on the starting time. Okay, and this is going to be optimal. I can't find any counterexample for this one. That's why I need to prove that this is going to give me the optimal answer. How I'm going to actually prove this? Let's say just simplify the algorithm in one way. After you sort the intervals based on the starting time, when you are actually looking for the color, remember the template was that you sort the activities based on some order, you ordered them, and then for assigning each activity to a color, the next available color. Okay, I'm going to simplify the algorithm and say that, okay, let's give a color to each, let's give a name to each color. So whenever I'm going to assign a color to the next job, I will find the color with the minimum index. Okay, I'm going to stick to this algorithm. That then in this way, if for example the color 1, there is no conflict with that, assign color 1. If there is conflict with that, assign color 2. If there is conflict with 2, try to assign 3. Okay, just try to find the next smallest color number and assign it to the job. This is going to give me this strategy, sorting based on a starting time, is going to give me the optimal answer. The time complexity of this algorithm, before actually going to the proof, the time complexity of this algorithm is going to be O of n log n. You know that sorting the algorithms based on the starting time is going to take n log n. Now the main question is this part, that for each job, you are going to find the next available color. How you are going to do that? If for each job, I check all of the colors to see if there is a conflict for it or no, I'm going to add another cost of, for example, if I'm going to use k colors, the time complexity of this loop will be O of nk if I just look for all the colors. But this is not good. This time complexity is not good. I'm going to actually try to find something better than this. I will leave this one as an exercise for you, but the hint for this one is we need to use a priority queue. We put all of the colors in a priority queue and actually update them based on the latest time of the job which has been colored by that color. So using a priority queue, this loop can be done in O of n instead of nk. So I'm going to get rid of this time complexity. So O of n and O of n log n, the total time complexity is going to be O of n log n. So, but the hint is that you need to use a priority queue. Try to write down the algorithm for this one using the priority queue, and if there was any question, we can discuss it during the class or in office hours. So let's just go to the proof of the optimality of this greedy strategy. The greedy strategy was to sort the intervals based on the starting time. I'm going to prove that. But before actually going to the complete proof, I'm going to give you one definition, which is going to be the depth. Over a set of intervals, I will define the depth to be the maximum number of intervals which all of them are running at some at a given time. Okay, so what is going to be depth in this example? You can see that I can find some time that there are two jobs running at this time. And if you look at all the times, you will see that if I check all the times, there will be at most two jobs at each time, which both are, all those jobs are running. So the depth is going to be 2. Let's actually have another example. The depth of this example is going to be 5. If you look at all the times, you will see that, okay, how many jobs are running here? 1, 2, 3, 5, 4, 5. If you actually just count all of each step of time, you will see that the depth of this set of intervals is going to be 5. This is going to be the maximum number of jobs that all of them are running at any given time. One observation about the depth over a set of intervals is that whatever is the optimal answer, it cannot be less than depth. You agree, right? Because you know that if the depth is whatever is the depth, if the depth is k, you cannot use k-1 color, because at least you know that at some specific time, for example, this one, you have 5 different jobs running. So at least I need 5 different colors. This is the key observation that helps me to prove the optimality of that strategy. Okay, now let's actually discuss about the proof. The greedy algorithm that works based on the starting time of the jobs, if it gives me an answer of k, I am going to prove you that there is not possible to find a solution with k-1 color. Why? I'm going to prove it to you that if the algorithm gives me k colors, it means there is some time that I have at exactly k different intervals, which all of them are running. What does this mean? This means that the depth is at least k. And if the depth is at least k, you cannot find an optimal answer less than depth, right? So this is not possible to find anything less than k. Whatever is the interval, whatever the greedy algorithm actually gives me is the optimal answer. So what I need to do is to show this part. I have to show that if the greedy algorithm gives me k color, definitely there is some time, I can find some time that k different intervals are running at the same time, at that time t. How I'm going to prove that? Let's just, the greedy algorithm tells me it needs k color, right? Let's assume that the time L or the interval L is going to be the first time that I'm using the color k. It means that not all and no other color is going to be available. It means that all of the other colors has been used for some interval, and all of those intervals are running, and now I need to use the color K. The greedy algorithm gives me this answer, right? So this is the first time that the color K has been used. So it doesn't matter where it happened, it just tells me that at some, let's just call this one the interval L, which the first time I am using the color K in the greedy algorithm. It tells me something, because the greedy algorithm always tries to find the color with the smallest color name. If it is using color K, it means that all color K, all the colors from 1 to K minus 1 has been assigned to something else, right? And at that specific, there is some specific time that all of these intervals are running from 1 to K minus 1. All of these intervals are running, and there are some specific time between the starting and ending time of all the intervals that there is a conflict. That's why I need to use the color K. Otherwise, if there is no such time, instead of K, I would use some other colors from 1 to K minus 1, one of these colors, right? So definitely there is some specific time T that all of these are going to be running. If it is the case, the depth is going to be definitely greater than or equal to K. And so far, I'm actually claiming that K is an answer. Greedy algorithm finds an answer, right? So K is the answer, and K is definitely less than or equal to the depth. And we already have this observation that the optimal answer cannot be less than depth. That's enough to prove that, yes, the greedy algorithm is going to give me the optimal answer. Here I'm done with the proof of the optimality for this strategy, but I have written 2 other strategies for you just as an exercise to check if they are optimal or no, and if they are not, you have to find a counterexample. One strategy, if they are optimal, if you claim they are optimal, you have to prove them. One strategy is to, we have already seen the strategy that sort the jobs based on the conflict in increasing order. Now, let's look at this strategy that sorts the jobs based on the conflict in decreasing order. So from the largest conflict to the smallest one. What do you think about this strategy? Is this going to be an optimal strategy or no? If no, you need to just find a counterexample. If yes, you have to prove that this is going to give you the optimal answer. This is one exercise, and the other one is there is another greedy algorithm here. This one, I'm going to give you this hint. This is not optimal. Try to find a counterexample for this algorithm. What the greedy algorithm actually do, this is trying to use the greedy algorithm for the job interval scheduling. It's telling you that to use that algorithm to find the maximum subset of jobs that they don't have conflict, right? Remember that algorithm properly gives you the maximum number of jobs that they don't have conflict. So this algorithm is going to use that algorithm to run over the jobs, find that set, give all of them the same color. You can, right? Because there is no conflict between them. Give all of them the same color, then remove them from the set, rerun the algorithm, repeat, again run the algorithm to find the next set of jobs that there is no conflict over them, and then give them a color, and then just repeat. This one, the intuition here is that you always try to find a set of the largest set of jobs that they don't have conflict and give them a color. But this is not going to give you the optimal answer, and but it is very nice exercise to work on the counterexample. Try to find a counterexample for this exercise, for this greedy algorithm. The next problem that I'm going to discuss is called total completion time. In fact, this problem is a kind of, again, job scheduling, but a different problem. So what is the problem? Assume that I have n jobs. Each of them, I know that how long it would take to process them, but there is no a specific interval for them, so I can reorder doing them. I have n jobs. I'm going to have to do all of them. I know that how long each one would take, and the problem here is to minimize the total completion time. So if I'm going to give you an example, just assume that I have, I don't know, 5 jobs. Like, let me give you some table that, for example, P1, P2, for example, P1 is 10, then 5, for example, 6, 2, I know, and 7. So if I'm going to actually do these jobs, just the order that I have them here, P1, P2, P3, P4, and P5. Okay, if I just do them in the same order that I have, the completion time for P1 is going to be 10. It would take, you started from time 0, right? So it would take, for example, 10 unit of time to finish P1. Then how much, what is going to be the completion time for P2? You have to wait for P1 to be done, then you can do P2. So it's going to be 15, right? And the completion time of P3 is going to be, you have to wait for P2 to be done, then you can do P3. This is going to be 21, 23 for P4, and 30 for P5. So the total completion time is going to be the summation of completion time for all the jobs, right? Here for me from 1 to n, it's going to be, in this example, if I follow the same given order, this is going to be 10 plus 15 plus 21. How much? 35, 56, 79, and 109 in this case. But you can see that I can find another ordering. This is not the optimal. I'm going to minimize this, but it is not optimal. If I order these jobs, if I first do P4, then P2, then P3, P5, and then P1, the completion times are going to be 2, then 7, then 13, right? You have to wait until P2 is done, then you do the P3, which is 6, it's going to be 13, and then P5 will be finished at the time unit 20, and then P1 will be finished at 30. So if you get the summation of all these numbers, the answer here is going to be 30, 20, 20, 72, which is way smaller than that 109. Okay, so the problem is that I'm going to order the jobs, so that the total completion time, the summation of the completion times are going to be minimized. The greedy answer for this, I mean, the greedy answer that gives me the optimal answer is that I just need to order the jobs based on the processing time. First, do the one that has the shortest processing time, and then just order them based on the processing time in increasing order and do the jobs in that way. It is very intuitive. What is interesting about this specific problem for me is that how we prove it. I'm going to just stick, explain the proof. This is a kind of proof. We have seen something similar to this, but it is nice to see more proofs, right? I just wanted to give you more examples of how we do the proof about a greedy strategy, show that a greedy strategy is optimal. So here the greedy strategy is that sort the jobs based on the processing time in increasing order. And I wanted to show you, to prove that this is going to be an optimal strategy. So again, I'm going to assume that there is an optimal answer, in which in that optimal answer, the order of the job is different than the order that the greedy solution, greedy strategy gives me. Otherwise, if it is the same, it means that the greedy is going to give me the optimal, right? I'm claiming that maybe it's not optimal. I'm going to show you that it is not possible. So assume there is an optimal solution which is different than the answer that the greedy gives me. This means that the order of the jobs is not completely sorted based on the processing time. So it means that there are two jobs in the optimal order, that PI and PJ. That PI comes before PJ, right? Then I is less than PJ. You are doing PI. Just assume that these are all the jobs that you are doing. There are some PI coming before some PJ, where the value of I is less than J. You are doing a PI before PJ, but the processing time, PJ is greater than, PJ is less than PI. PJ is less than PI. Okay, and the rest of the jobs. Okay, this is the optimal answer. Okay, I'm claiming that if you change the order of these two jobs in your optimal answer, you get a better answer. I'm going to focus on all these jobs between PI and PJ, and I'm claiming that by changing the processing PI and PJ, you can get a better answer. Why? Because after you are changing PI and PJ, the job that will be done here, the completion of this job is going to be whatever is the completion time here. After you are done here, which is going to be, let's just call it C of I minus 1, right? C of I minus 1. If I do PI here, the completion time of PI is going to be this, right? Instead of PI, if I do PJ, the answer that I get is going to be CI minus 1 plus PJ. I already know that PJ is less than PI, so definitely this completion time is going to be less than this completion time. How much less than? It is going to be exactly whatever is the value of PI minus PJ. So this difference is going to affect all the jobs here. This is going to be something that will be decreased from all the jobs between PI and PJ. So by changing PI and PJ, I'm going to get a better answer. This is kind of actually contradiction with this and the optimal answer. And this this template for proving that your greedy answer is optimal is called the exchange argument, exchange discussion or argument. The thing is, we get whatever the greedy solution gives us and compare it to the optimal solution and show that by doing some exchange, either you get a better answer, so it shows that the optimal answer is not optimal, it is a contradiction, or in some cases you would show that okay, by changing the optimal answer and trying to actually make it more like the greedy, you are not making it worse. This kind of proof you have seen similar actual argument in the knapsack as well, remember? So the next problem that I'm going to discuss is called minimize the maximum lateness. Again, this problem is about some jobs we are going to schedule. So what is the problem? Here we have n jobs. There is no interval associated to them, but we know that how long it would take to do them, and we also have some deadline for them. So this is just an extension of the previous problem. Not only I know about the processing time, I also have some deadline to finish the job. And I wanted to do all the jobs. So the problem here is that I wanted to minimize the lateness on all the jobs. How can I define the lateness? The lateness is actually defined as how much delay, how much late you are doing it after the deadline. Okay, so for the job I, assume that you have some ordering of all the jobs. Whenever the job I has been done, let's just actually call it CI. You finish job I at the time CI. If it is after the deadline, it means that you have some lateness, right? So that's why I rewrite the formula as the maximum of CI minus DI and 0. So if you do the job, if you complete the job before the deadline, this is going to be negative, and so it's going to be, the lateness is going to be 0. What I'm going to minimize is the lateness of all the jobs. This is not the summation or something. I just wanted to minimize the maximum lateness. So let me give you some example. These are 6 different jobs. I have some processing time for them, how long it would take to process them, and some deadline associated to each one. Job 1 takes 3 hours, and the deadline is at time unit 6, for example. Job 2 takes 2 hours, and the deadline is at 8. So this is going to be an ordering. Just assume that I am doing job 3 first, so, and then job 2, job 6, job 1, job 5, and job 4. How I can actually calculate the lateness? Job 3, the processing time for that is just 1 hour, for example. So and the deadline is 9, so the lateness is going to be 0. The lateness for job 2, after you are done with job 1, so the completion time, let me just write down the completion time and the lateness, all of it. The completion time here is 1. The completion time of job 2 is going to be, after you are done with 1 plus 2, it's going to be 3. The completion time of the job 6 is going to be 5. The completion time of job 1 is going to be 8. The completion time of job 5 is going to be 11, and the completion time of the fourth job is going to be 15. Now I can calculate the lateness. The lateness for the second job, the deadline is 8, so the lateness is 0. The lateness for the sixth, the deadline is 15, so the lateness is 0. For the one, the deadline is 6, so the lateness for this job is going to be 2. The fifth job, the deadline is 14. It is still actually greater than 11, so the lateness for this job is going to be 0. And for the last job that we are doing, the 4, the deadline is 9, and you are finish it at time 15, so the lateness here is going to be 6. So the maximum lateness is going to be 6. But what is the optimal strategy to actually sort these jobs in some order that minimize the maximum lateness? I'm going to again check a couple of greedy strategy. The first one is that we are going to order the jobs based on processing time. Okay, it is similar to the greedy strategy that we had for the previous problem, which was minimizing the total completion time. And I can simply just find a counterexample for this. This is not going to give me the optimal answer. Why in this example in this table that you can see, the processing time of the first job is 3, the processing time of the second job is 2. So it tells me to order the jobs based on the processing time. It means that you will do D2 first and then D1. So based on that, the lateness for D2 is going to be 0, but the lateness for D1 is going to be, the deadline is 1, but you are finishing it at time 5, so the lateness is going to be 4. Although I could get a better answer, right, by first doing the first job. If I did D1, then if I did the first job and then the second job, the lateness for the first job will be, it would take 3 steps to finish, so the lateness will be, there will be some lateness anyway for this job. The lateness for this one is going to be 1, and the lateness for the second job is that the completion time is 5, so the lateness for this job is going to be 2 as well. Both of them will be delayed, but the maximum lateness is 2. So this is a better answer. The other greedy strategy is that we can order the jobs based on deadline minus the processing time. The intuition here is that it tries to find some way to involve the deadline and processing time, both of them. So it tries to order the jobs based on the difference between the deadline and processing time. Again, this is not going to give me the optimal answer, and I can find a counterexample for that. This is the counterexample. I have 2 jobs. The processing time of the first job is 1 and the deadline is 2. The processing time of the second job is 10 and the deadline is also 10. So the greedy strategy here tells me to order the jobs based on the D minus P, the deadline minus the processing time, that if you actually calculate it here, this is going to be 1 for the first job and 0 for the second job. So the greedy strategy tells me to run job 1, then job 2. If you do that, the lateness of the first job is going to be 0. So the lateness for the for the second job is going to be 0, the first job that you do. But the lateness for the second job is that the completion time of the this job is going to be, you need to do job 1, then job 2. So the completion time of the job 1 is going to be 11. So the difference between the 11 and the deadline, the lateness is going to be 9. And it is clear that the optimal answer is different. The optimal answer is to first do job 1, then do job 2. So in this case, the lateness of job 1 is going to be 0, and the lateness of job 2 is going to be only 1. The completion time here is going to be 11, minus the deadline 10, the lateness is going to be 1. So this is way better than the answer that the greedy strategy gave me. So what is the optimal greedy strategy? It is to order the job based on the deadline. Try to always do the job that has the earliest deadline. Okay, let me just run this over the first example that we saw. If we ordered the job based on the deadline, you can see that, okay, first job 1 will be run. It is actually already ordered based on the deadline. So job 1, job 2, 3, and so on. The lateness of job 1 is going to be 0. The lateness of job 2 is going to be 0. The lateness of job 3 is going to be 0. The lateness of job 4 is going to be 1 because the deadline is 9 and it will be completed at 10. The lateness of the job 5 is going to be 0 again, and job 6 is going to be 0 as well. This is better than the answer that we saw here, right? That the lateness was 6. So now the question is, how can I prove this greedy strategy? Give me the optimal answer. The greedy strategy is to sort the jobs based on the deadline in increasing order or in non-decreasing order. There is no difference. Okay, so I'm going to emphasizing on that non-decreasing because sometimes some of the numbers are equal, right? And it is important in our proof. So how to prove this? I'm going to just assume there is an optimal answer, okay? Always there is an optimal answer, sorry. There is an optimal answer that it ordered the job, but the order is different than the order of the greedy algorithm, which means that the jobs are not ordered in non-decreasing order, okay? So it means that I can find 2 jobs, let's call them the job K and K plus 1, that the deadline of job K is greater than the deadline of job K plus 1. If it is less than or equal, it will be exactly similar to the optimal, to the greedy strategy order, right? But I'm going to assume the optimal answer is different than the greedy. So it means that I can find 2 jobs. I mean, let's just stick to 2 adjacent jobs. That the deadline of K is greater than deadline of K plus 1. So let's now calculate the completion time compare it the optimal answer with some other answer that I am exchanging these 2 jobs. Okay, so basically I'm going to just exchange these 2 jobs. It means that I'm going to do the K plus 1 first and K second. With this assumption that the deadline of K is greater than the deadline of K plus 1. I can write probably this color, I don't know, I don't really quite like this color. It's just to use a different color here. Red might be more readable. Okay, one thing that I know about, let's just assume that the previous job that has been done before here is going to, let's just call it the completion time of this is going to be C of, for example, K minus 1. Okay. Everything until CK is the same. In this new solution, I'm going to just change the order of K and K plus 1. So I wanted to know that what would happen to the latency of the jobs after changing these two numbers, these two jobs, K and K plus 1. One thing that I know about the finish time of the job K before changing the answer is that the finish time is going to be whatever is CK minus 1 is plus PK, the processing time of K. I don't know anything about the processing time of K, okay, but that's fine. What is going to be the completion time of this job? This is going to be the completion time of PK plus 1. So whatever here I have, plus the processing time of K plus 1. So the processing time, the completion time of K plus 1, I know the formula for that. I know the formula for the completion time of K as well. Based on this, I am going to calculate the latency as well. The latency for the kth job is going to be the completion time of the kth job minus the deadline. And the latency for the K plus 1 is going to be the completion of the K plus 1 job minus the deadline. Okay, I have calculated these two formulas. I'm going to exactly do the same calculation for this new solution. That the only difference between this S prime and S is that I have changed the order of these two jobs. So now I can calculate the completion time in this new order. Let's just call this C prime K, the completion time of the kth job, although this is the K plus 1 in the previous order, but this is the kth job in this S prime, right, after changing the order. And the completion time of K plus 1 job, so it's going to call it C prime K plus 1. I can write these formulas for C prime K and C prime K plus 1. By comparing CK and C prime K, you can say that, okay, I cannot really, comparing the formula, I can say that I cannot really compare these two values because I don't know what is the processing of K and K plus 1. I just know about the deadline, but I don't know about the processing time. So I can't conclude anything about CK and C prime K, and therefore I cannot say anything about the latency of the kth job in the original optimal solution and in this one that I have exchanged the jobs. But what about C prime K plus 1 and CK, these two? You can see that all the terms are actually the same. So C prime K plus 1 and CK plus 1 are the same. So I can do some conclusion about the latency of the K plus 1 job, right? I can just compare this one and this one because I can simply just say that whatever is PK and PK plus 1, the processing time, it is appearing in both terms, so I can just remove them, right? And by comparing the latency of the K plus 1 job in the original solution and in this new solution that I have, I can say that yes, L prime, the latency of the K plus 1 job is going to be less than or equal to the latency of k plus 1 j in the original. And the reason is that dk is greater than dk plus 1. So you see that I'm actually subtracting them, so I can conclude this. The latency either is going to be equal, so maybe both of them are not late, okay? Or the latency in this case is going to be better. I still cannot say that this difference, this change is going to change the maximum latency in the optimal answer. Maybe it is 0, maybe the maximum latency is happening somewhere else. But yet this exchange is going to tell me something, that whatever is the optimal solution, if I do this change over the jobs, if I have 2 jobs that the order of them are not actually matching the order in the greedy in the greedy strategy, if I do the change and make it similar to greedy, I'm not hurting any, the optimality part. I'm making it either better or don't really change it. Because of this, I can keep doing the same exchange over all those pair of jobs that the deadline in the order of the deadlines is not matching the order of the deadline in the greedy solution. And by doing all of those change, making the optimal solution either better or not actually hurting it, okay, and make it exactly like the optimal solution. That's enough to prove that yes, the greedy strategy here, which sort the jobs based on the deadline, is going to give me an answer which is optimal. So far, and this is a kind of exchange argument again. I started from the optimal, compare it with the greedy strategy that I have, and by doing some exchange, try to actually from the optimal reach to exactly the same answer that the greedy strategy give me. In this way, I can prove that the greedy strategy is optimal. I'm done with the discussion about greedy algorithms. We have seen 6 different problems, maybe more. And we have seen many different greedy strategies. Some of them doesn't work. Prove it using some counterexample, and show you the proof for the optimal strategies. I'm going to just conclude this video by summarizing the 3 different approaches to analyze the optimality of your greedy choice, your greedy strategy. These are not complete. It doesn't mean that if you're going to prove, you should definitely follow one of these approaches, but these approaches are very popular when you are working on a greedy algorithm and you wanted to prove the optimality of your greedy strategy. So for example, the structural one, you will find some structure around on your optimal answer, and by showing that your greedy strategy exactly follow that structure, you can actually prove that your greedy strategy is optimal. An example of this one was, remember, for the job interval scheduling, we find some observation. We define the depth, and that observation about the depth proved that the greedy strategy just exactly follow that structure. That was an example of this structural proof. Or the exchange argument that the previous problem, we have seen it a lot. The exchange argument is something very popular when you are proving the optimal, when you are proving the optimality of your greedy strategy. Or the first one is the approach that we have done over the coin changing problem, that you always show that your greedy algorithm is going to give you at least as good as the optimal answer, any optimal answer that you can have. Okay, for the readings, these problems that I have discussed here are coming from your textbook, section 1 and 2, and also from the again I forgot the name of where the K come from, but the Tardush Katie textbook, the section 4.1 and 4.2. Although I'm going to finish the discussion about the greedy algorithms here, but next week, and when we discuss about the graph algorithms, we still are going to see some example of greedy algorithms. In the graph algorithms, we will see some example of dynamic programming as well. So the problems that can be solved using greedy algorithms or dynamic programming are not restricted to this kind of problems. We definitely come back to them and see more examples of greedy algorithms and dynamic programming.